In this paper, we present gaze-guided hand-object interaction synthesis, dataset, and method. Gaze is rich with intent information. See an example of assembly furniture. We observe that exploring the consistent relationships among gaze, hand, and object can enhance our understanding of human activities in fine-grained scenarios. Besides, gaze can benefit VR and assistive technologies, like playing chess with gaze and gestures in Vision Pro, or helping cerebral palsy control games using gaze. Motivated by this, we propose a novel task, gaze-guided hand-object interaction synthesis. In this task, the initial hand-object pose and gaze serve as the input, and the corresponding hand-object motions are generated as the output. This task is particularly well suited for integration into VR or AR environments and assistive technologies to gain a new gaming experience. However, there is a lack of suitable datasets. Therefore, we collect GazeHOI, the first interaction dataset that simultaneously incorporates 3D modeling of gaze, hand, and object interactions. Here are examples of some sequences. For data collection, we use ZCAME2 for hand tracking, OptiTrack PX13 watts for object tracking, RealSense D455, and PupilCore for ego and gaze tracking. For data annotation, we utilize MediaPipe to extract 2D hand keypoints from each view, followed by triangulation and mono-model fitting. We scanned a set of objects and attached 3 mm markers to them to obtain the object pose from OptiTrack raw data using the ICP algorithm. Combined with gaze from ego view, we obtain a set of fully annotated data. We propose a novel task, gaze-guided hand-object interaction synthesis. Addressing this task is challenging. We propose a novel approach, a stacked gaze-guided hand-object interaction diffusion model, named GHO-Diffusion. We decouple the task into two stages, gaze-activated object dynamics synthesis and object-driven hand kinematic synthesis to reduce the complexity of motion generation. We propose a spatial-temporal gaze feature encoding approach for the diffusion condition to generate object motions. Then we leverage object motions to synthesize the corresponding hand motions by hand diffusion. Since the hand diffusion effectively captures the overall distribution of hand-object interactions, it falls short of achieving precision in finer details, such as maintaining contact or avoiding penetrations. Therefore, we leverage the guidance strategy in sampling. First, we define 3 guidance functions from the perspective of kinematic, contact, and penetration. The naive guidance strategy directly adds the computed gradient to the sample and may misalign the final motions with the original data distribution, resulting in unnatural motions. So we introduce HOI-Manifold Guidance to strengthen the physics constraint while preserving the original data distribution. Then we get the hand-object interaction sequences. Motions generated by diffusion do not always fully conform to the gaze distribution. We also select diffusion results based on consistency scores between gaze contact maps and gaze interaction trajectories. Next, we will present the experiments. We choose MDM, Text2-HOI, and OMOMO as our baselines. Quantitative results demonstrate that our method significantly outperforms the other baselines. Here are some visualization results about our method and baseline on scene complex objects. Here are some visualization results about our method and baseline on unseen objects. Thank you.